Good morning, fellow virtual ICCEers. My name is Ab van Dongeren, and I'm going to give a keynote talk on waves on reefs, on how coral reefs transform ocean waves to help protect coasts. My name is Ab van Dongeren. I work at Deltares and also at IEG Delft in the Netherlands. Coral reefs help protect coastlines in tropical areas. They protect atoll islands, which are very low elevation islands where everybody lives less than 3 meters above mean sea level. They also protect most tropical high islands like Pago Pago in American Samoa, where most of the population lives below 3 meters because the rest of the island is too mountainous. They also protect mainland coasts of large countries and continents with high population densities along coastal margins and plains. So these islands and coasts are vulnerable to wave and wind-induced flooding, and therefore they need the protection of coral reefs. Some of the problems that these low-lying areas are facing are sea level rise. And the sea level in the Western Pacific has already increased 2 or 3 times the global average, as you can see at this top plot in these dark colors. And the total sea level may rise by 20 centimeters to 2 meters by 2100, with large regional differences. And this is, of course, a big problem for these low-lying atolls and low-lying areas. At the same time, we face coral reef degradation due to fishing, pollution, ocean acidification, and warming, which have caused the loss of reef area, but also the loss of reef cover. And then there's population growth, which has increased tremendously on some of these islands. And here is an example of eBay on the Kwajalein Atoll, which is overpopulated, has tens of thousands of people living on an area of about 2 kilometers by 250 meters in width. So not only do the hazards increase, but also the exposure of people and assets, and therefore the risk and the damages. So we need to understand how the wave transformation on these reef-lined coasts is different from more familiar sandy shores. And the main difference is in the difference in geomorphology. Here's a map of Roi Namur, where you see that there's a deep water blue that rises up quickly. The bathymetry rises up quickly to a horizontal shelf, which is very inhomogeneous and can sometimes be very rough. Another difference between sandy shores and these islands are that here the waves break on the reef edge at quite a large distance from the coastline. So here we have narrow shelves and we have steep coasts, which means that the surge is not as important and the wave-driven processes are, which is visualized here, where the surge in blue is a function of the slope, and the milder the slope, the more important the surge is. And the wave-driven components are in red, and that's the inverse. So the steeper the slope, the more important the wave components are. So we need to understand how the waves are transformed, how the breaking takes place, how the wave transformation takes place, and how the run-up and the flooding takes place. And that sets the stage for this talk. Here I'm going to be talking about different aspects of the wave hydrodynamics or the wave dynamics and run-up on these steep island coasts. Here we have a conceptual figure of a reef slope leading up to a reef edge, a reef flat, the shoreline, and an island. And here are some waves. Here are waves in wave groups. As you may know, every 7th wave is a high wave, which may break on the reef edge. And that produces setup, but also sea swell, infragravity wave, and very low frequency component waves. And they're defined in the field as such. Sea swell waves are typically between 5 and 20 seconds. Infragravity waves are between 25 and 200 seconds, and even lower or longer period waves are called very low frequency waves. Now combined, the setup and these wave components will produce run-up, overwash, and flooding onto the island. So first we'll talk about wave breaking on the reef edge. There have been a number of field and particularly lab observations. Here on the right you see observations made by Mark Buckley of a reef profile of a deep reef, a steep slope, and then a reef flat, over which the sea swell waves, the short waves, shoal up and they break violently on the reef edge and dissipate and losing a lot of energy. But in the meantime, there are these longer period components, the infragravity waves and the very low frequency components that here ramp up on the reef edge and then propagate onto the shore and have about the same wave height. This is when you're considering a smooth reef, but if you have a very rough reef, as was shown by Justin Rogers, bottom friction also plays an important part. So, and it can be more effective in dissipating waves than wave breaking. And with models, we've been able to capture the integral processes, the bulk wave height with pretty well with simple wave energy based models using a constant gamma. Gamma is wave height over water depth. But the details of the wave breaking and the transformation of the sea swell waves, the infragravity waves, is not captured well with these simple models. So we need to use advanced models, about which I will be talking a little bit later. But particular here, or very of interest here, is that the details of wave breaking may be known in the lab in a 2D situation, but they are not known very well in the field. So we need more observations of wave breaking there. So what happens on the reef flat? First we'll talk about the water levels on the reef flat. That's composed of a number of components. One is the astronomic tides. Those are pretty well understood and can be forecast. Then there are sea level anomalies due to ocean circulation, and they can also be forecasted better and better with models and Earth observation. The issue is that they need to be downscaled to small islands. The wind-driven component, the surge may be small, and the largest effect is the inverse barometer effect. So when the air pressure is low, the sea surface comes up. And this is only important in case of a direct hit of a typhoon on an island. But in general, the wind-driven setup is much smaller on these islands due to a lack of a continental shelf. So a very important part of the total water level on the reef flat is the wave-induced setup. And the wave-induced setup has been found to be proportional to the breaking wave height, as is illustrated here on the right. The higher the breaking wave height, HF, the higher the mean water level. And this is a paper from Janet Becker of 2014. You also see that it's inversely proportional to the water depth. So the smaller the water depth, the bluer colors, the larger the wave setup. And this is because in a smaller depth, the radiation stress term is larger, causing larger setup. So if you have small offshore water levels, waves breaking on the reef, you have a little bit larger wave setup. So what happens to the waves on these reef flats? And here I have an example from a relatively narrow reef flat, less than 400 meters, of the island of Funafuti in Tuvalu in the Pacific Ocean. And this is a paper by Eddie Beetham of 2015. And what we see here is that the sea swell wave heights are controlled by the tidal level. Tidal level is here on the horizontal axis, and you see that the sea swell waves increase in height as the tidal level increases. They're also a function of the offshore wave height. The higher the offshore wave height, the higher the sea swell wave heights at the shoreline. What we see is that the infragravity waves are not very much tidally controlled, but they are driven by the offshore forcing. So it doesn't matter that much how high the water level is for the infragravity waves. They're more dependent on how large the forcing is offshore. The higher the offshore waves, the higher the infragravity waves at the shoreline. And here we see what we saw before, is that the setup is inversely proportional to the tidal level. So the setup is largest when the tidal level is smallest. Now, is that generally true? No. There is a difference between narrow and wide shelves. And as an example, I have an analytical model developed by Mark Merrifield and Janet Becker that predicts the infragravity wave height as a fraction of the wave height at the reef face as a function of a parameter delta. And delta is a coefficient that is determined by the friction, the damping, D, the width of the reef, L, and the depth over the reef, flat. And as you can see, for large deltas, which are rougher or wider or shallower reefs, the infragravity wave height is limited. And that's because of friction. So friction is very important to understand, especially for wider reefs. And it's one of those parameters that we don't know very well. We don't know very well how to transform a given coral cover into a friction coefficient that we can put into a model. On the left, you see that for narrow reefs, the response is quite scattered. So there's other processes going on, for instance, resonance, that influence the infragravity wave height as a function of the reef parameters and also the forcing. So now I'll move on to modeling. How can we model these processes? And we have a number of models that are available. I discussed 4 types here. First of all, you have the wave stationary models. So and that's a top plot over here, they produce a steady wave height and a steady setup. So for instance, Swan or XBeach stationary are 2 models that can do that, or any energy model will do the same. One step up are the models that are wave group resolving. They don't compute the surface elevation of the individual waves, but rather the amplitude variation of the wave groups, but they do compute the infragravity wave, which is the black line over here. This is the slow modulation of the sea surface in time at larger timescales. One model that can do this is, for instance, the hydrostatic model by XBeach, the surf beat model. And then here at the bottom you have the wave resolving 2D models like XBeach non-hydrostatic or SWASH, which do resolve the sea surface of the short waves. And all the way at the bottom, here's an example from Ryan Lowe. This is a smooth particle hydrodynamic model which resolves 3D motions, and for instance open foam or these SPH models can deal with this. So how well do we predict wave transformation? This is a plot from a recent paper by Ellen Cotard and myself and Kurt Storlazzi, analyzing the computed wave properties across a reef in Roi Namur, the same case that I've shown before. And there are a number of stations here, which we plotted here, the forereef, the outer reef, the mid-reef, the inner reef, and the northwest, and the outer and the mid-reef in the northeast. And then we plot the mean water level, the setup, and the sea swell, infragravity wave, and very low frequency components of the wave height. And we see that for the surf beat model in red and for the non-hydrostatic model in blue, we do a fairly good job of predicting the wave heights and the water levels and the setup. We see that the sea swell wave height is over-predicted a bit by the surf beat model, and we also see that we're under-predicting the very low frequency components. But all in all, we can do a fairly good job of predicting this wave transformation. There are also more advanced hydrodynamic models, such as smooth particle hydrodynamic models, in which individual particles or droplets are interacting with each other. So here is a model with about 1 million particles. And where you can see that with these particles we can resolve the 3D structure under the waves and also the individual wave breaking and the overturning waves. And this model already shows good comparison to laboratory data. Now that we can compute wave transformation, we can also compute wave run-up on islands. And here's an animation, an XBeach animation, showing the run-up on a Philippine island during Typhoon Haiyan. And you see that the run-up is about 6 meters, while the steady setup is only 3.5 meters. So here the oscillatory components are much more important, or as important, as the wave setup. We also know that the wave run-up is controlled by the reef parameters. And here's numerical data from the same case run by Shimozono, who shows that the reef width, as the reef width decreases, the run-up increases. But the problem is that run-up, we don't have much data. We have video stills, as shown here, from Roi Namur. We have some debris wreck lines from the same case in the Philippines, and we have now a video from Hawaii. But we need more run-up observation to validate our models. Because even though the wave transformation is done relatively well, we still see that both non-hydrostatic models here in blue or the surf beat models here in red underpredict the observed wave run-up here in gray. Nevertheless, we can already start making assessments of wave flooding, as we've done here for the island of Roi Namur. And here you see waves coming from the left, which is from the north in this case, and I'll advance the movie a little bit to show that we now can do flooding over these low-lying islands. And this is for a scenario of RCP 8.5, so business as usual, with a sea level rise of 0.8 meters in 2055, which causes severe flooding already. We can do the flooding, but what we're missing are lagoon effects, so waves coming from the lagoon, we're only looking at the ocean side, and also the groundwater infiltration, so how the salt water infiltrates the aquifer. And we can do this for these small islands with these high computationally expensive models, but how do we do this for larger areas and more islands? And we need a reduced physics flood solvers. So what have we seen from this presentation? There are a number of missing observations and data. We have a need for better physics and better models, but we also have a need for simpler and faster models. So on the observation side, we need more deep water wave buoys and Earth observations, especially in remote oceans like the Southern Pacific. We need field observations of wave breaking. We only know how the waves break in the lab right now. And I know that's difficult to measure, but it's something that is of great interest because the wave breaking controls how the waves will transform and how they will propagate towards the coast. We need to know the reef bathymetry and coastal topography, not only just in a few isolated places, but also across the ocean. And remote sensing, like the ISAT-2 satellite information, could be of great help there. We need to observe run-up on steep islands. As I've shown, there's only 3 cases where this has been done, and we need to do that more consistently. And we need to collect historical and anecdotal flood data. We need to know what happened in the past in order to judge whether future conditions are hazardous or not. And there's a big wish list on the better physics and models. We need to describe the wave breaking and the roller and the setup effects better because we're under-predicting these right now. We don't know yet exactly how to parameterize reef roughness. Given a certain reef canopy, what's the roughness, the friction coefficient that is associated with it. We can go forward and we can say we can include these reef structures in our modeling, and then we have to develop canopy models, which is already happening, but this is something that we need to develop in the future. I've only talked about the hydrodynamics here, but the morphodynamics, how the coast will erode, has not been dealt with, but already efforts have been made in that direction. We haven't done much about the interaction of groundwater aquifers. So how does the salt water penetrate into the soil and salinize the groundwater aquifers, which are needed for agriculture and drinking water? We need to look at the wave and surge effects in atoll lagoons. And we need to look at what the effect is of reef channels. So not all reefs are homogeneous along shore. They are bisected or intersected by reef channels. And we need to understand how reef resonance is triggered. And in order to upscale, we need to go to, we need to understand the physics, but from the physics, we need to go to simpler and faster models that capture the essentials. We need faster wave transformation on complex coasts, faster flooding models, but also meta models. So models that are based on either data, observations, or numerical data in order to give us a quick answer. With faster models and better data coverage, we can upscale to the globe and derive a global early warning system for these tropical islands. For instance, we can use satellite-derived reef geometry, not only for Roi Namur as I've shown here, but for the entire world, or all the small islands at least, and combine that with forecasted offshore water levels in waves, and then drive the Beware model to produce run-up estimates anywhere on small islands. Of course, we need to combine that with a reanalysis of historical water levels in order to estimate what the return periods were and what safe and unsafe levels are. But with those three ingredients, we can produce these flood alerts anywhere on the coast where they're not existing now. So the science, the faster models, and the better observations will all lead to a product that could be really useful for people on tropical islands. This we're trying to drive with the Blue Planet Oceans Initiative, Deltares, NOAA, and USGS in a group called WaveForce, which is open to the public and open to colleagues who would like to collaborate on this. So this is an invitation to join our WaveForce group. I'd like to thank Kurt Sturlatzi of USGS and Ryan Lowe of the University of Western Australia for providing slides for this presentation. This concludes my keynote talk. Do you have any questions? Let me know. I can answer them in the following session or by email, seen below. Thank you.